Okay, let's check out a long answer problem regarding galvanic cells, electrochemistry. These can be a little tricky, but let's take a look. We are given a standard galvanic cell. We have a copper electrode and a tin electrode. As current flows through the cell, the student determines that the copper electrode increases in mass and the tin electrode decreases in mass. So, identify the electrode at which oxidation is occurring. Explain your reasoning based on the student's observations. So what is happening? What is oxidation, first of all? Oxidation is a loss of electrons. So clearly at one of these electrodes, we have neutral atoms that are being oxidized to form ions that then fall off of the electrode and enter solution, right? So that's why the mass is decreasing. So if the tin electrode is decreasing in mass, what that means is that some of these tin atoms are being oxidized, right? The electrons are flowing through the wire over to the copper electrode, and the tin 2+ ions that result are falling off of the electrode to join solution, to enter the solution, right? That's the oxidation. What that also means is that over here, the copper electrode is receiving the electrons, and it is able to do that because copper 2+ ions are leaving solution to be deposited onto the copper electrode. The copper 2+ ions in solution accept those electrons. They are reduced. They're becoming neutral copper atoms that are joining the copper electrode. So the copper electrode is increasing in mass because more copper atoms are getting on there. And the tin electrode decreases in mass because tin atoms are falling off, because electrons are being removed and then the ions fall into solution. So, so oxidation is occurring here, right? This is the oxidation, and this is the reduction. Right. Half reactions are separated in a galvanic cell. As the mass of the tin electrode decreases, where does the mass go? Well, we just answered that as well, right? What we're saying is that the tin ions that result from the oxidation are leaving the electrode and entering solution. They're entering this solution over in this oxidation half reaction. Now, we want to understand what the salt bridge is doing as well. In this right here, we're looking at the salt bridge. Draw and label a particle view of what occurs in the salt bridge as the cell begins to operate. So we just want to show it's a potassium nitrate salt bridge. So we have potassium ions and we have nitrate ions, and they're in that salt bridge. And remember, those are going to move in such a way so as to maintain a charge balance, right? Because we have positive ions that are joining solution here and positive ions that are leaving solution here. And so that's going to cause a charge imbalance, right? So how does this work? Well, as positive ions are leaving solution here to deposit onto the copper atom, well, potassium cations can go down here, right? These can go down here to balance that out, right? We're losing positive ions, so more positive ions enter and balance that out. Likewise, here it's a little different, but if we have more positive ions joining solution, we cannot remove them, but what we can do is add more negative ions, and that will maintain the charge balance this way. So here, all we have to do is show that potassium ions are leaving the salt bridge to enter the reduction half reaction, and nitrate ions are leaving the salt bridge to join the solution in the oxidation half reaction. And that is how charge balance will be maintained, which is the purpose of the salt bridge. Okay, so that's that. A little bit more to talk about here. This part says a non-standard cell is made by replacing the 1 molar solutions of copper nitrate and tin nitrate in the standard cell with 1/2 molar solutions. So those solutions there that are holding the electrodes, we have copper nitrate and tin nitrate solutions in there of a particular molarity. The standard cell says they're 1 molar, right? That's just a standardization that we use. But it doesn't have to be, right? So we could also have half a molar solutions in there. So the questions that follow, right? So the volumes of solutions are the same, but the concentrations are cut in half for the non-standard solution. Is the cell potential of the non-standard cell greater than, less than, or equal to the cell potential of the standard cell? So what we need to understand here, this may or may not be intuitive, but the reaction quotient here, we're just talking about, right, we're producing tin 2 plus ions, and we're using up copper 2 plus ions. So it's really just about this ratio, right? So whether we put in 1 molar and 1 molar or half a molar and half a molar, it doesn't really matter. If the concentrations are the same, that is not going to change the reaction quotient, and that is not going to change the cell potential, right? So this is going to be equal. This is going to be equal. It doesn't matter how concentrated or dilute. It's just about the relative concentrations of those ions. So that one will be equal. Now, on the other hand, both the standard and non-standard cells can be used to power an electronic device. Would the non-standard cell power the device for the same time, a longer time, or a shorter time as compared with the standard cell? So here we are getting more quantitative, because in order for this cell to power a device, right, the current must be flowing. And the only way for the current to be flowing, remember that we're oxidizing those tin atoms, and the electrons are flowing through the wire over to the copper electrode, but that can only work. The electrons only have somewhere to go as long as there are copper ions in that solution, in that half reaction, that can receive those electrons and become reduced to become neutral copper and join the electrode, right? So when those copper ions run out, the cell is done. It cannot power anything anymore. There can be no current if there are no copper cations to receive the electrons on the other end. So here it does make a difference. It's going to run for a shorter time because the copper ions are going to run out faster. There's only half as many. Right, so this is a good question. This part is good because it's making you think about if the solutions are more dilute, what does that affect exactly? Right, it does not affect the cell potential. We're just talking about a potential with the current, right? The voltage of the current that will result, which will be the same as things are getting depleted. But one will get depleted faster because there's less of it, right? So that's a good one. Now this says, in another experiment, the student places a new tin electrode into a fresh solution of 1 molar copper nitrate. And so here we have some information. We want to write a net ionic equation for the reaction between the tin electrode and the copper nitrate solution. That would be thermodynamically favorable. And so it's really the same thing, right? We're just saying that copper 2 plus is reacting with neutral tin to produce neutral copper and tin 2 plus, right? And this is aqueous, this is solid, this is solid, this is aqueous, right? We do want to include those. So this is just what's happening, right? Copper 2 plus is taking 2 electrons from tin to produce neutral copper and tin 2 plus ions, right? And so now what we want to do is we want to get the cell potential, right? The standard cell potential. And so what we understand here is that we've got copper 2 plus going to copper, neutral copper. So right, E cell, that's going to be, we're going to take that one, that is the reduction. And so that is going to be 0.34. And we're going to subtract from that the other half reaction. So tin going to tin 2 plus. Now, this is negative 0.14. Remember, it's a little counterintuitive that we would not flip this. But remember, this negative sign right there, that's doing the flipping for you, right? By subtracting it, we are taking into account that it's actually tin going to tin 2 plus, rather than tin 2 plus going to neutral tin, because we would add these, right? We would add what's going on in these two half reactions together, but this negative sign takes care of that. So always E cell. We're just going to take the two values from the table and plug them into our equation precisely as they are. That can be a little confusing, but if you can remember that, it makes things very easy, right? We don't have to change anything. We just have two numbers, put them in. That's all there is to it, right? And we want one that's thermodynamically favorable. We need a positive E cell. So even if you forgot which one goes first, you'll know which one is going to be the right one because we need a positive E cell. A positive E cell is thermodynamically favorable. It's spontaneous. A galvanic cell means a spontaneous redox reaction. This is supposed to go on its own to produce a current, right? So we would not put it the other way around. We would get a negative number, and that would not be spontaneous. So we do that, and we get 0.48 right volts, 0.48 volts. So that's E cell for this galvanic cell. And remember, justify that the reaction is thermodynamically favorable because E cell is positive. If it wasn't, it would be going the other way, right? Because one way is going to be positive, the other way is going to be negative. Now calculate the value of delta G for the reaction. So here we need to know which equation we're going to be using. So this is going to be this one here, where we have negative NF E cell. So N is the moles of electrons that are involved in this process. F is Faraday's constant, and E is this E cell, right? E cell is the cell potential. So what is that going to be? Well, we have the negative from right there, and then we have 2 moles of electrons, right? Right here, we know that we're talking about 2 electrons being transferred. So we do need to put a 2 right there. And then Faraday's, we can look up 96,485 coulombs per mole of electrons, right? The charge carried by a mole of electrons. And then we're going to multiply by our E cell, which is 0.48 volts. And if we recall, volts is really just joules per coulomb, right? So moles of electrons, coulombs, those cancel. We end up with negative 93,000 joules per mole, or we would say negative 93 kilojoules per mole. So that would be our delta G, standard delta G there. So this is a very good question here. We talked about galvanic cells, oxidation, reduction, what is going on in a galvanic cell. We definitely have to understand what's going on with the neutral atoms, with the ions being deposited as neutral atoms and the neutral atoms falling off of the electrode, joining solution, etc. What's going on with the salt bridge, and then this other stuff with standard solutions versus non-standard solutions, calculating E cell, and then calculating delta G with that. So that was a bit about galvanic cells.